Beautiful. All right, we are recording. Well, hello everyone. Just a couple overall announcements. In case you've mentally forgotten, Dash is next week if you've signed up for it. And if you're like me and have a presentation or a poster to give, make sure to get that done and turned in soon for the folks organizing that. And then this is also going to be the only telecon we have of October, just with meeting schedules and things being a bit wonky. We'll have another telecon the first Monday officially of November. And the week following that is going to be the PyHC meeting. So that'll take place November 11 to 13 here in Boulder at LASP, also on Zoom. And if you're also interested in staying for the Science Data Systems workshop, that's going to be the Thursday and Friday of that week. So just keep that in mind. And that's all I have right now. Sean, do you have anything you want to say?
Um, Not really my announcement to make, but I could mention that we have 14 job applicants for our HSSI proposal.
True, true. We do have that, and Sean and I are meeting to go through them a little bit later today. So that's pretty exciting.
Yep. And this is the heliophysics software search interface for people who forgot that acronym.
Yes, yes. And then Rebecca and Catherine are involved in that effort. Rebecca's on the call right now too, on the metadata side of things. So soon we'll have a student to work with you on.
Woohoo. But yeah, short of that and reminding people of Dash, I do not have anything else this morning.
All right, sounds good. Yep. Schedule for the SDS workshop available yet? No, but we met finally last week. We have been going in between a bunch of different schedules, one of which being the lead organizer's wife having a baby last night. So it's been an interesting path to making this meeting schedule happen. But it will be coming out very soon, Rebecca and everyone. Cool. All right. Well, without further ado, I want to go ahead and turn this over to Hector, who's graciously agreed to be on the telecon. You all saw, the long title in the email, but I'm going to let Hector go ahead and explain all of that better himself.
All right. Thanks, Julie. Let me go to kick things off. Gotta share the old screen, and I'm gonna share my entire window because I have to give you all a live demo. So I believe y'all should be able to. Oh, give me the option to do failures. Can y'all see my screen right here?
Yes.
All right, just want to make sure. So yeah, I'm gonna give you all a presentation and was it a tech demo of was it basically a periodicity detector I worked on at NASA with my mentors, Nicolene Weil and Simone Di Matteo, who are here in this call right now. So basically, its title says periodic signal detection by the adaptive multi-taper method. It's basically another type of Fourier analysis tool. So let's just get things kicked right off as to why we developed this tool in the first place. And that basically, that there is a oh no, the Windows that there's basically a uh, basic baked-in issues with just using standard Fourier transform algorithms by themselves. And there's this issue called spectral power leakage. And what it is essentially is it's specific to analyzing just finite data series just by themselves, in which the window which the data series is defined over acts as a was it a data taper, so that you get these edge effects, these flaring and ripples whenever you just perform just a Fourier transform on the data itself. So I had to exemplify this issue. We have an example of just a pure sine wave. I hit it with a square box type taper to emulate just the window itself. It would show up just with the data by itself, but we wanted to exaggerate it. And when you just do a just direct fast Fourier transform, just a pure sine wave, you get, obviously, with a Fourier transform, you'd ideally get a single data point, but instead you get this flaring and rippling around the frequency resolution. And that's what the leakage issue is. Of course, there are ways to mitigate that by using special tapers. This one's called the Slippian sequence. And just using one of these tapers, you just mitigate the power leakage completely. And this leads into basically what the multi-taper method is all about. Next screen. Here it is. It's basically, it's called the historically, spectral concentration problem. How do you ensure that all your power is maximally concentrated within a user-defined bandwidth? And these Slepian sequences, they were made in the 70s by one aptly named Slepian. I don't know what his first name is. I couldn't find it in his papers. They're a set of, they're an orthogonal set of eigenfunctions that were designed to do so. And then David Thomson brought those functions and to Fourier analysis. And as the name says, multi-taper, you can use multiple tapers to mitigate leakage and also solve that issue of spectral concentration. And also, it compared to regular Fourier transform algorithms, you reduce the variance, as you can see in these bottom three panels, where we have some noisy time series defined with a known power spectral density. We then performed a fast Fourier transform in this orange plot in the middle, and then the multi-taper method transform. You can see here the variance in the multi-taper is much smaller compared to the FFT. And just to give you all a rundown of how it actually works, basically right here, we have a noisy time series. It's white noise with a sine wave embedded in it. The inputs that you would give to it would be basically your X data, the corresponding time array. Then you just define what bandwidth that you would like. It's expressed as a NW, where W is like an integer multiple, or it's a multiple of like your frequency resolution delta F, but it's defined as NW. Once you define that NW input, that gives you the max number of tapers that it automatically defines. It generates those tapers, multiplies that, slaps those tapers onto the time series, gives you K amount of independent tapered power spectrums, and then they're recombined in this final result on the right-hand side right here as the multi-tapered power spectrum in this what defined with a weighted average. And a special thing about this is I know I'm just showing time series here, for example, but this can be, it's Fourier analysis, so this can be a
Just Sean and I, or did Hector freeze? Okay.
I think we've completely lost him.
Oh, there. It looks like Hector. Oh, he's smiling.
Can y'all hear me?
Oh, there you
There you are.
Did I cut out? Oh no.
All good, all good. It was maybe like 10-ish seconds. So
All right, that's it. Let me just reshare this. Y'all can let me know what's the last thing you remember. What,
Previous slide, please.
this one?
Yep, you were on the first column.
Dang.
I know how you feel.
No,
Give it a shot.
okay, no worries. Basically, this is how it works. You have some time series that you want to analyze. I have this example, sine wave, white noise. Inputs, X data, corresponding time array. You define your bandwidth, expressed as NW. It's an integer. That, once you define that, it's usually greater than 2. You don't need more than 2 or 3 NW. This gives you the max number of tapers it generates. It generates those tapers. You can see in this middle plot panel right here. And then it does the whole taper the time series, creates the Fourier transform. You have K amount of these independent tapered power spectrums. And then they're recombined on the right-hand side as a weighted average based on what's called the spectral weights. Because if I didn't mention before, these tapers are, as Slepian mentioned in his paper, it's they all follow this long eigenvalue problem. So they have a corresponding eigenvalues. Then you have this power spectrum. And what I said while it was cut out was that, Fourier analysis. So this can be applied to any type of data series, not just time series. It's just up to me and you, the user, just to know what that Fourier frequency corresponds to. Y'all can still hear me, right?
Yep.
Yes.
Okay. So in addition to a power spectrum, the multi-taper method also has a way of built-in way of detecting periodic signals using phase coherence. How it does is essentially it takes this here time series, one of just a simple sine wave at a constant frequency, constant phase, embedded in locally white noise. It just, again, performs the whole multi-taper power spectrum aspect, multi-taper calculations, but compares that to the actual power spectrum that you're wanting to analyze. That essentially just sort of models that sine wave to this here, analyzed power spectrum. And it gives you this here, what's called the f-test. It's basically, in essence, is looking at the phase coherence. If you have a matching frequency that perfectly models the power spectrum you're analyzing, then you get large values right here. This is the case, again, sine wave 8 hertz in noise. You can see I just sort of highlighted in the middle power spectrum plano. And you can see here as this large spike here in the f-test right here. You just an extra note that while this is a good way of detecting periodic signals, you can yield false positives like this small one right here. And these merely just come from violations to the fact that this here test sine wave is in locally white noise. And why that's important is for when it comes to real data analysis. So this here, was it identifying signals in noisy spectra? Turns out most real geophysical data, specifically, this comes from climate scientists, geoscientists, that they exhibit in their power spectrum, they exhibit this red noise profile. You can see on these right plot panels, these are just electric and magnetic field magnitude measurements. We applied, the multi-taper method to it. You would exhibit the same profile where you just have high power at low frequencies. It doesn't even necessarily need to look like this, but just follow this trend. And these bottom two right here is what happens when you have actual periodic signals within this profile. So this was it's been a known thing in climate science and other geoscience fields, but namely aptly Michael Mann and Jonathan Lees. They're looking at periodicities in climate time series and developed a procedure basically to pick out to determine if these little enhancements in the power spectrums were indeed periodic signals, and essentially follow this here 3-step process. Firstly, once you have your multi-taper power spectrum, you're going to go ahead and model the background noise spectrum, BK. They used an autoregressive one function because that was a good model for estimating red noise back in the day. Then they compute the confidence thresholds of what's called the gamma or amplitude test. It's merely the ratio of your power spectrum to the modeled background spectrum, and the harmonic f-test. So you in essence have a dual test for the power spectrum. What is that noise in the back? And basically, if you have a peak simultaneously past both of those, then that signal is indeed to be a periodic. Don't worry, I'll show you an example in a bit. I just need to give quick credit and shout out to Mann and Lees because they devised this procedure. They had an extra step that I didn't mention where they, once they made the multi-taper spectrum, that they smoothed it out, but it's optional, as I'll mention. And just give credit, this procedure that they did led to one of the first papers finding the anthropogenic source of climate change. So, as a quick example, I have two here. One, a heliophysics example. It's done by my mentor here, Nikki Vial. She was the first to just apply Mann and Lees procedure to heliophysics data, specifically solar wind density, where you have here the amplitude tests or the gamma tests, the corresponding confidence thresholds right here, and the dashed lines right here. And the bottom is the f-tests with their confidence thresholds. You can see by the dots right here in the f-tests and the dash that those are what it looks like for simultaneously passing tests. On the right here, we have from our Python periodicity detector, just a simple example of artificial red noise with a sine wave baked into it. Right here is the time series of that frequency right here. The corresponding multi-taper power spectrum. You see it follows that red noise trend. I just highlight where the peak is. And then to the right, we have the f-test and the amplitude test with the dual confidence test. And see it passes right here, the 0.125. So before I go on into more details and giving you a demo of the Python, I have to give one last piece of credit and shout out because this here entire Mann and Lees procedure, it already exists. And it was done by my other mentors here, Simone Di Matteo, who adapted it into IDL and made it even more modular. This here plot is just an example of how it's done. The time series up here, the power spectrum with some background models. And then we have here this or I believe it's smoothing. And then we have here the gamma and f-test statistic with their confidence thresholds. And the extra features that Simone added just to make it modular was there's multiple smoothing options. You can either just use the raw power spectrum, medium smoothing, log, bin, Butterworth, and also instead of just using the AR autoregressive function as a background model as Manlees did, you have additional into it. You have there's a white noise solution. If you have white noise, they use power law and bending power law. And as these are good, the power laws are good models for estimating red noise. In addition, the Simone's code has been widely used aside from heliophysics and other sciences. What's interesting that I found was they use it in sports science. So analyze head impact injuries, and they're of course still using geoscience. There's a study looking at water vapor analysis to look at the climate in Argentina. So now we get into the Python routine, and just a few things about it. It currently has no smoothing options; those are coming, and it just has white parallel and bending parallel for the background fit. So let's go on to the demo. I believe y'all can still see my screen. Someone please confirm.
Yeah, we can see it.
All right. So now, all right. Well, first things first that you're going to do is you're going to go ahead and install my Python package version 1.01 as of yesterday. And we're here to have this little test script. So essentially, once you have that installed, you're just going to want to go ahead and import the package like this here. All these other extra packages, just extra plotting modules, the way it's currently designed is like you just extract data arrays and you can use whatever custom plotting preferences that you'd like. So once you import that, I'm going to go to do that. And just as a word to mention that I'm going to be using 2 noise models for the data you'll see. You'll have here a white noise for some time series and a red noise generated by an AR1 autoregressive 1 function. So the first thing, the first major function of this package is, as it says here, it's called get ATM specs. Basically, what it will return is like the corresponding Fourier frequency, the multi-taper spectrum, this quantity called alpha, which is called half degrees of freedom. It's used for the background fitting, and the f-test. The inputs, all you would have to use is your corresponding data series, whatever it is, its corresponding time array. This here string input called ACH-full, it basically gives you the option to either return a one-sided power spectrum, assuming that you're dealing with real value data, or just like the complete dual-sided, full-sided power spectrum. And then you'll define the bandwidth NW right here. In practice, I basically have here in practice, it's basically right here. I define my NW as 3 because that's my favorite number. And I define my time series up here. I believe, what did I do? I did a 12 hertz sine wave? Let's go ahead and run this function right here. So right here, I have here just a noisy sine wave. I'm using white noise, I think, right here. It's 12 hertz. You can see right here in the corresponding power spectrum in this middle plot panel. I went ahead and just went ahead and just plotted SK versus the Fourier frequency, and I just highlighted the 12 hertz. And on the right side here, we have the f-test, as mentioned. I can also do this for red noise, just to show y'all what it looks like. Just go ahead and change this noise profile. And there we go. Here it is with the red noise profile right here. Again, it's the same sine, 12 hertz sine wave. As you can see, it has that, high power at low frequencies. Again, you can see the peak right here, and again, the f-test right here. So that's the first major function of what you call it. The next one, the most importantly, is the background modeler, the get PSD fit. As I mentioned, there's 3 options. There's a power law, there's a white noise, and which is an analytical solution for like a single scalar, and then the bending power law. So what this function will return, because it comes after the get ATM specs, is it will give you the frequency, the Fourier Fourier frequency axis that you want to perform a background fit over. It'll give you the BK, which is the modeled background spectrum, and it'll give you fit parameters. It'll just give you like an array telling you the optimized coefficients for the specific model to use. And the inputs would basically be those ATM spectral products, the frequency, power spectrum alpha, the type of fit that you want to do. NW and F range is basically frequency range that you want to perform a model over. And in practice, again, I believe I'm using this time, I'm using the same 12 hertz sine wave, and we'll do it for, let's do it for white noise. So right here, again, you just call get ATM specs, and then down here, we're going to down here, we're going to do bending power law. We're just going to use the default option for S range in. I'll show you because it gives you some print statements, and then you're going to call get background PSD fit. The stuff below is for extra plotting, just to make things look pretty. And once you do that, a few things it's going to tell you. Should mention this: when you get ATM spec, it tells you, hey, it's creating the multi-taper spectral plots. NW equals 3, K taper equals 5. It'll tell you, okay, you're fitting over the default frequency range. Turns out we exclude the 0 hertz frequency and the Nyquist frequency because they don't follow the same distribution as the multi-taper method. But that's extra details aside. It'll tell you what that corresponding frequency range is, tell you optimizer method that's used, and it'll give you the optimized coefficients for that background model right here. Of course, this is white noise, so let's go ahead and change that to get an accurate depiction. Change this to red. And right here, the coefficient, here's the noisy sine wave right here on the left-hand side. On the right-hand side, here's the power spectrum in red noise. And orange right here is the bending power law fit and the coefficients displayed. And of course, as I mentioned, you can change this. You can use the power law solution. And you get the optimized power parameters for the power law. Right here, 0.85, 1.19. Additionally, if you'd like to look at a specific frequency range, not just the background, you can change this to say, let me look at 5 to 20 hertz. And you'll get an altered print statement where it says using the default, it says, so user chosen frequency range, 5 to 20 hertz. And you'll get something like this. Of course, this is a known AR1 type of noise profile, not a bending power law profile. So the choice of your background model will affect how your background is estimated. So, and then we get lastly, and this is still a, I won't say work in progress because the function's done, just to have made a function to compact this all into one, basically computing the confidence thresholds from the gamma test that I mentioned before, the F test, and then finding their overlap. And this, it's a bit much, but basically there's 3 functions. It's called get F test comps. It returns to you, at least for now, the time being, 3 confidence levels, the 90, 95th, and 99% confidence levels. I've yet to add the option to get it custom because we're still testing this out. There's another one, get gam test comps. It does the same thing. The inputs will be almost the same. You'll just have, like, again, the inputs you input, it would be the background fitted frequency axis, the F tests, the bandwidth NW, the F range if you're looking at this particular fit. For the gamma test, you'll have to input the power spectrum, the background fit, and those other things. And then to find the dual confidence test, you have to input, well, here it's made it modular, so you can look for either the 90, 95, 99. You just have to input the correct inputs, and that being the background fitted frequency axis. Then now defined as a gamma test array, the F test, and the particular F test. Oh, all these words. The F and gamma test confidence levels that you want, and that will give you this here, these here 4 data products. Really, it's this last one that matters, FG peak freq, because that tells you the frequencies in which they intersect at. So that word gerbil aside, we're going to apply this to this here. We're going to, We're going to have 2 sine waves at 2 different amplitudes and 2 different frequencies, one at 0.1 and 0.3. And we're going to embed it in, again, the AR1 red noise. So this is what the time series will look like. So I have the same data. Well, 0.3, I'll just make it 0.4 just because. And in practice, it's going to look like here. You'll have your get ATM, your get background, and then these 3 functions right here that just extract all the, confidence levels for the F test, the gamma test, and their overlap. And then everything below is for plotting stuff to make it look pretty. So make this 0.42. So once you run it all, you'll have this, kind of like that, It'll give you some extra text right here about finding the overlap right here. And down here, I have it such that it returns the index locations and the intersecting frequencies it occurs at. So we have noisy sine wave, red noise, 0.125 hertz, 0.42 hertz. Down here, the corresponding, multi-taper power spectrum. Here we used a bending power law to model it. You can see both of the peaks right here. Here's the 0.25 right here, the 0.42. And then to the right, we have F test and gamma test. And you can see it's indicated by a green star. I'm not sure how well y'all can see it, but that's the intersecting in the F and gamma test. Just exactly what we get. I have it displayed right here. It's at 0.125 and 0.42 about. So yeah, that's a demo on how to use this. Let me go ahead and switch my slides back. And that's pretty much it, y'all. I have two QR codes. The first is to the PyPy website with the Python package. The second is to my mentor Simone's, the IDL version, because as I mentioned before, that's done and made, ready for anyone to use if they have IDL, want to use IDL. Currently, we're beta testing the Python package just to make sure it's just as good and modular as the IDL routine. And if y'all have any extra ideas, just let me know. The PyPy QR code also leads to my GitHub page, which has a tutorial, not the tech demo, but an actual tutorial on how to use it. And much more in-depth detailed tutorial on how to use all these functions. And also it has the tech demo uploaded there. So you can go ahead and check that out. And yes, that's it, y'all.
Thanks, Hector.
Yeah, no problem.
All right. Do we have any questions for Hector other than the ones in the chat?
Yeah, Hector, could you post the name of the package in the chat again?
Yeah, no problem. Let me the package. I'll post the link if that helps to the PyPy page, if that's all right.
Sure. I just I'm opening an issue as we speak to get this added to PySpeed-S, so I'd like to have the name of the package.
AMTM signal detect. And yeah, as I mentioned before, it's still being updated and worked on. Yeah, so there's the PyPy link to that.
Awesome, thanks.
Jen, did I just hear you say get this integrated into PySpeed-S?
I discussed it with my advisors about it, and we thought it might be best. Originally, it just integrated just into the the PyHC, just have it be a standalone. But yes, it can be integrated with PySpeed-S if need be. I'm open to integrating it into PySpeed-S, but it can just be a standalone. Right, as of right now, it's just a standalone package.
Yeah.
I mean, I think there's a couple Brian Harder packages like that, if I'm remembering correctly. CDF-lib or something like that, that are technically PyHC standalone as well as being in PySpeed-S.
Yeah, that's correct. They had the CDF-lib and actually PyTplot is for the moment standalone, although we're about to absorb it into PySpeed-S.
Oh, cool. It's good to know. All right. Well, if there aren't any other questions, Rebecca, do you want to maybe voice some of the ones you put in the chat?
Sure. So could you go back towards the beginning of your presentation where you were showing the first peaks and there was a false positive?
Yeah, this one right here.
Yeah. So you've shown a lot of plots since I asked my question, so I feel like it's partially answered. But how that false positive, well, without any dash marks to guide me,
I know.
um,
I know.
it
Sorry.
looks
Where's
no,
my
it's
arrow?
fine. It's fine. But you've begged the question now. It looks like a harmonic, like the frequency over 2. However, I don't see any other harmonics showing up anywhere. So I tentatively believe that the method deals with harmonics quite well, but still this false positive shows up. And some of your later plots almost look like harmonics, but not quite. Maybe you could
Oh,
help
like
with
these
that.
ones right
No,
here?
not that. That's obviously not really a harmonic in my mind.
Okay, but this
Um,
first one?
yeah, that one, and then there was some stuff later on. What is your understanding of how this method deals with false positives coming from harmonics?
From harmonics? If it's coming from, at least from my way of understanding how the F-test works, because if it just solely from the F-test, if it isn't a harmonic, I do believe it would show up as a distinct periodic signal in the F-test. But this is also the reason why we use both the F-test and a gamma test. Like uh, we say, we determine it to be a periodic signal if it passes both, because the gamma test does not share the same false positives as the F-test. But it's funny because I have been looking at some harmonic data, but I haven't paid attention to the F-test to see how it shows up. And as your question to see how it handles it, as of right now, I don't know. I'd have to.
So I can help with this,
Oh,
Hector,
thank you.
Yeah,
or
go
maybe
ahead.
Simone wants to chime in too. But well, first of all, in this plot, that's actually the wrong direction for harmonic. Harmonics actually go on this plot should go to the right, not to the left. So twice, so a factor of 2, but the other way. So that's the first thing. The second thing, harmonics can really be in a signal, right? Like in the magnetosphere, that's they really could have both a 1 millihertz wave and also a 2 millihertz wave because of the physics that's really there. And in that case, it really will show up, as Hector said, in the F-test, you'll see it in both places. And in the multi-taper spectral estimate, you'll get power. If there's enough power at both places, you'll see it show up. Sometimes what'll happen with a physical signal that has a harmonic is like the primary mode will show up with a lot of power and the second one won't have a lot of power. And so then you'll see it in the F-test because it'll be really phase coherent, but you won't see it so much, the harmonic in the multi-taper method. In terms of ringing though, where you have a primary signal and there really isn't a harmonic, but you have some beating with the noise or whatever, that the multi-taper method is specifically designed to damp down anything like that. It's one of the features that's so awesome about the multi-taper method. So it really does a nice job of eliminating ringing and effects like that.
Okay, cool. So my question comes from exposure to oscillations in astrophysics. So I was surprised that wasn't even a domain that was mentioned. So if you haven't already thought of it, talking to some people in astrophysics that study oscillations and do the Fourier analyses, that would probably be a really good audience for this.
Okay. Yes, I haven't. I think when I was looking at the citations for somebody's paper, I don't remember if I saw. It was a long weekend. Don't remember if I
Yeah.
saw there. I think some astrophysics. I wanted to make sure that the people citing Simone's paper were actually using the tool and not just referencing his paper.
Yeah, that's hard.
But yeah, yes.
Does anyone know if AstroPi does some oscillation stuff? I've been out too long. Crickets. Okay, so that's worth looking at. I have a different question if no one else does.
Yes. What is your question?
Okay, completely on the code side. So you were starting with an IDL code. Did you try to convert it to Python using, say, ChatGPT 4 or something, or did you just go for it?
So no. So it turns out I actually forgot to mention them. Do I have it still in the tell me I was a genius and left this credit. Here we go. So it turns out this is as discovered by Simone, but the actual multi-taper power spectrum was not developed by me, but it's developed by another person, German Prieto. we use their multi-taper package, and one of the things we were doing currently right now was comparing if the steps and spectral data products are, how similar are they to what Simone did in IDL? And because he already devised this Python package to make the multi-taper spectrum. What we did in our Python routine was just the Mann and Lee's, adapted the Mann and Lee's approach, which was what Simone did in his paper, which was the whole, all right, now do the whole, you have your multi-taper spectrum. Now do the whole model the background, and then find the confidence levels of both the F test and the gamma test, and see if there's any overlap. That's what we did for this Python routine. The multi-taper package already exists as a standalone package as devised by Prieto, but we just brought his work here and just combined it with the Mann and Lee's procedure.
Okay, thanks. Interesting.
Hello.
Hi.
Excuse me. Actually, I'm from India, so I'm a master student of physics. So can I take help from the PyHC for my final project of my master's?
Yeah, my GitHub is up. I really should work on my PyPy page, but
So
if
I
you
need a guide for that. So,
don't worry, if you
uh,
hit the home page on the PyPy link, it leads to my GitHub right here, and it has the tech demo and a tutorial on how to use
okay.
this. Things are
I
still
need a
work in progress on the
actually a
doc.
guide for so I'm not like I'm a physics just I'm learning, I'm a student, no, so I need a guide for that. So can anyone help me for that? So to like about like for it's a master's thesis kind of a thing. So that
Sorry,
I want
is this related to work that Hector has been presenting, or are you asking just generally for something that's unrelated here?
yeah. Uh, Still like so how to take the help of anyone, so like I'm good with the Python and other stuff like Matplotlib and Pandas, NumPy. So I'm looking for so that I can apply this to the real world project.
Um, I think that might be out of scope for this meeting, I'm sorry to say. I mean, if it's related to the like what's been presented here, maybe Hector might be willing to help with some things, but if you're seeking general help or doing generic Python things for your master's studies, that's not necessarily something that we do.
Yeah, yeah. Thank you.
You're welcome.
Are there any other questions for Hector on the material presented?
Oh yeah. I'll just be on this slide. QR codes.
I guess then you mentioned, that this officially has a version number and so forth. I think you said as of yesterday, which congratulations on. What's the timeline for being interested on submitting to PyHC?
Um, I know, I remember, was it, I still need to work on the documentation, and maybe February.
Okay, yeah, I was just curious if it was like this year, next year, just more generally. So
I
cool.
think February.
We'll be on
Beginning
the
of spring would be
lookout
a good time.
for that.
Yep, no particular rush, but it seems like you would fit in great among our projects.
Appreciate it. Appreciate y'all asking questions. Like I said, it's ready to be used. It's ready to test it. And, I didn't even talk about, but it has some good. And I mean, I need to discuss this with with my mentors, but it does perform better in some regards than IDL. But that's comparisons and paper writing aside. Um, And yeah, if you have any questions about the package, go ahead and hit me up by email. It's the QR codes for Python package and the ideal one if you'd like to use that one. But yeah, that's pretty much all I have to say.
Awesome. Well, I'll just ask one final time. Any questions remaining for Hector? Okay, cool. Well, his email will be attached in the replies, so you can get at him that way. And I believe that's all we have for today. Just a final reminder, Dash is next week. The PyHC meeting will be November 11 to 13. That's a Monday to Wednesday. And if you have not registered, please do so that you can be sure to get communications about this in the future for the upcoming meeting. And thanks again, Hector, for presenting on all this today.
Thanks, everybody. Appreciate it. Please use it if you do Fourier analysis, or let people know about it.
Awesome. Thanks, everyone.